Here at Armstrong Atlantic State University's Network-Enabled Workspaces Lab, we are interested in the research and development of visual haptic simulators to improve the teaching of abstract science concepts. In this video, we will describe our recent visual haptic simulator, which demonstrates gyroscopic motion using commercial haptic devices. Here we see a real-world example of gyroscopic forces. This bicycle wheel is suspended on its axis by a rope and spun by hand. The wheel seems to defy gravity because the large amount of angular momentum due to its rotation makes it much harder for gravity to rotate it in a perpendicular direction. The net result is that the wheel's axis of rotation moves around in a circle. This effect is called precession. Here we have another example of a gyroscopic system. This is another demonstration of the principle of conservation of angular momentum. When we tilt the wheel horizontally, we change the direction of the wheel's angular momentum. This imparts opposing angular momentum. When tilting the wheel left, conservation of angular momentum forces her to spin to the right, and vice versa. We've developed a haptic space simulation to help students gain a better understanding of how gyroscopic forces work. Using haptics, we have the ability to physically touch and interact with artificial environments. Humans obtain information and interact with the world via our five senses: sight, hearing, smell, taste, and touch. We commonly use displays for sight, speakers for hearing, and a keyboard and mouse for input, but this really limits our ability to touch and completely ignores the senses of taste and smell. Using haptics devices like the Sensible Phantom and the Novint Falcon, we can feel simulated objects as if they were real. Combining multiple modes of sensory feedback has been shown to increase student learning, so we're hoping that the additional mode of touch that our simulation provides will complement the traditional teaching of angular momentum concepts. For this project, we used Extensible 3D, or X3D, Python scripting, and the H3D application programming interface developed by Sense Graphics. H3D is an open-source, cross-platform scene graph API that uses OpenGL for graphics rendering and HAPI for haptics rendering. Our simulated environment demonstrates the conservation of angular momentum with a hands-on approach. Here we see the simulation running on dual Novint Falcon devices. The wheel on screen was created in 3D Studio Max, then converted into X3D to model a real bicycle wheel. The wheel moves freely around the environment as users physically manipulate the haptic devices. The menus on screen allow users to modify and adjust variables that affect gyroscopic motion. When the user applies torque to the wheel, counter torque is sent back to the haptic devices, pulling the user in the opposite direction, demonstrating how forces applied to a gyroscopic system are accompanied by equal and opposite forces. We accomplished this by trapping pointers inside very small cylinders at either end of the handle and wrapping a larger single handle around these. When the user manipulates the dual haptic devices, the pointers press against the inside of the small wrapping cylinders, causing forces and torque to be applied to the virtual wheel. Our goal was to develop a visual haptic simulator to enhance student learning by providing the ability to study abstract concepts, in this case gyroscopic motion, in ways that are traditionally not possible. For more information on this simulation, and to find out about other visual haptic physics simulators, please check out Dr. Felix Hamza-Lup's Network-Enabled Workspaces website. Thanks for watching.